Okay, continuing where we left off, we have learned that the derivative of e to the x equals e to the x. And I kind of like writing it this way. The derivative of d over dx, e to the x equals e to the x. The next thing we'd like to investigate is the derivative for the natural log of x. We know that e and natural log are inverses, and so this is natural. We're going to start with these. So it turns out the derivative for the natural log of x, to just show you why it is what it is, it's a lot more in depth than the derivative of e to the x. So I have it all written out here on my paper, but I'd rather not go through those details. I usually, when I'm teaching in person, I sort of make the judgment call whether to show it or not, sort of in the moment. Sometimes I ask if the class would like to see it, and oftentimes people say yes, they do want to see it. That said, I'm not going to spend the time working through it all here in this video. If you'd like to know why the derivative of the natural log of x is what I'm about to tell you, that is in the book, or certainly you are welcome to come to office hours, or maybe if you can't make office hours, you send me an email and say, hey, I'd really like an explanation for that. Then I can do a quick video and post that like separately for those who are interested. So here it is. What is d over dx of natural log of x? All right, and so here's all of my work. Turns out it's a good idea to reference the definition of e, and it turns out you have to kind of rethink how you do that as part of this explanation. To kind of give you a hint at the depth here. So of course I'm not going to read through all this, but you can see, okay, we're working with the log. We got some fractions in there. We're talking about a certain thing where this sort of ideas come in, and eventually, see, I have this note to myself: is this too much to present? Like, is this really beneficial for students? And some I think it is beneficial, but others it just leads to more confusion than it would have been had I just told you. So that's what I'm going to do here. Um, Turns out when you get the derivative f prime of x, it's 1 over x. So right there's the answer to this fill in. D over dx for the natural log of x is 1 over x. And that's really surprising. You would think that the derivative of a natural log would somehow involve a natural log. Right? You would think there'd be a natural log in the derivative, but there's not. It's very strange. Okay, let's see it in an example. And okay, I'll just kind of pull this up. Looks like I put a few examples sort of scattered on my page, so I don't want to show you all of it at once. Here we go. Example, how about y equals 6 natural log of x? What's the derivative of 6 natural log of x? Think, okay, well, it's got that constant multiple, 6, and I know the derivative for natural log x, so that's 6 times 1 over x. But we might not give this as our final answer because we can multiply those together and just say y prime equals 6 over x when we multiply them. Like that. Okay, I've got another example right over here. This one's a little bit harder. How about y equals the natural log of x to the third? Now this one is a bit tricky. You think natural log of x to the third? I don't know. I mean, I know the derivative of natural log x. What do we do if it's x to the third? So it turns out there are some properties of logs that you learned back in algebra. One of them was if you've got the log, sometimes you see like the log of base a. Let's say it's like x to the m. Sometimes you see these kind of letters. We call what's inside here the argument. If your argument is x to the m, you may remember you can move this number out in front as a coefficient, and those are equal. That's one of the properties or laws of logs. And it kind of almost feels like you're taking a derivative there. That's very close to the power rule, but of course it's not a derivative. These things are just equal to one another. Well, we can do that here. We can take that 3 and move it in front. And it's still y at that point, no derivative yet. Y equals 3 natural log of x. And then it's, like this style, right? It's got the constant multiple. And so then our derivative is 3 over x, and I wrote it as dy over dx just to mix up the notation a bit for us, give us some practice. Dy over dx equals 3 over x there. Okay. So let's, here I've got a couple things. Again, I'm writing out these derivative rules again. We're going to do this once in a while. We're just going to make a big list of all of the derivative rules that we've learned at any given time. Just kind of refresh our memory since these are so big for the course. So we've learned these two already. What are these arrows? It's kind of the progression, right? So we start with this one. Once we learn this derivative, I skip the explanation, but that helps us figure out this derivative. And then you see the arrow is going to continue. What else are we going to learn? So we have an exponential and a log, but specifically e to the x and natural log x. But there are lots of other exponentials and lots of other logarithms. So we want more general formulas for any given log or any given exponential, and that's what I'm about to show you. And let's talk through these one at a time. So once we have the derivative for the natural log of x equals 1 over x, again, I'm skipping the explanation, but that would help us figure out the log of x with base b. So that's a logarithm with any given base. And you may recall the natural log has a base of e, the natural number. So hence the connection here. But now we say, okay, no longer base e, but any base. And turns out this is the formula. Very similar to natural log. Natural log is 1 over x. Any other logarithm with base b is 1 over x times the natural log of b. So you still have that 1 over x piece to it, but then also in your denominator, multiply by the natural log of whatever that number is. Okay. We'll see an example in just a moment. Once we have this, that would lead us to, again, skipping the explanation, would lead us to figure out the derivative for any exponential. So an exponential is a number raised to the x. So if we have any number b raised to the x, well, what's that derivative? And it turns out it's b to the x times the natural log of b. So we see the connection even this way and this way. So e to the x is just e to the x. B to the x, we still repeat it. We still have b to the x, but then multiply by the natural log of b in just the same way as this denominator here. It's still 1 over x, but then multiply, still copy itself, but then multiply by the natural log of b. It's kind of interesting. It turns out that the e to the x and the natural log of x are special cases of these more general formulas. But we point them out because we see the derivative for e to the x and natural log of x much more frequently than we'll see these derivatives. But of course, we need to know how to do them if they were ever to come up. Okay, so those are the 4 new derivative rules for this section. Let's keep going with some examples. Let's do one of this style here. Let's go with y equals the log of x with base 3. And we're just going to follow the pattern. Okay, it's 1 over x, and then I see a 3 there, so natural log of 3. Y prime, 1 over x times the natural log of 3. And there you go. Let's see an example of a different type of exponential. This one has base 5. Y equals 5 raised to the x. Well, it's off the screen now, but we're just going to follow that formula. So it repeats, right? Y prime equals 5 to the x, but then we multiply by the natural log of 5. And there's that derivative. Okay. We did this example earlier, so I need to keep going. And we're going to wrap up with these derivatives. Find the derivative. They're a little bit more challenging than those that we've just seen. Let's start with this. We're just kind of putting everything, kind of starting to mix the pot. Every type of derivative that we know, could be thrown at us and blended together in any way. So let's start with y equals 4 times the log of x plus x to the 7th. Well, x to the 7th, I know how to do that. How about 4 log x? Now, when you look here, when it's just the log of x, I don't see a number. I don't see the base. Hey, if they don't write it, what is it implied to be? You may recall it's base 10. We call that the common log. If it's not written, it's assumed to be 10. Okay, so let's follow the rule. All right, so y prime 4 is a constant multiple, so it just carries down. Derivative of log x is 1 over x natural log of 10. And of course, x to the 7th plus 7 x to the 6th. And you might write the final answer. You might multiply that 4 up to the top and say this right here, y prime equals 4 over x natural log 10 plus 7 x to the 6th. Very nice, very nice. Now, certainly in problems in homework and things, you might need to plug numbers in for x. They might want an equation of a tangent line or a slope of a tangent line, or they might phrase it as find the instantaneous rate of change. Lots of different ways this could be presented. Let's do one more, part B. We got a note over here that's not really necessary right now. G of x equals 3 times 1 plus the natural log of x. And I highlight this one just to make a point. A lot of students want to begin this by distributing that 3. Nothing wrong with that. You can distribute that 3 first and then take the derivative after it's simplified. Or you could just leave the 3. Think of it like a constant multiple of the whole thing. And that's what I my note, right? Constant multiple times f of x. F of x here is what's inside the parentheses. So g prime of x, we can go straight for it. The 3 carries down. And the derivatives are 0 plus 1 over x. And then we could write our final answer. We're going to get this same answer no matter how we do it. 3 over x is our answer here. Okay. Hey, that's 3.2.